In today's class, let us learn how to write a Maxima program for finding the Taylor's infinite series expansion or Maclaurin series expansion of given function. Now we know what is the statement of the Taylor's theorem. Taylor's theorem says, suppose f of x is a function defined on the closed interval a comma b such that the derivatives f of x, the derivative of f of x, f dash of x, etc. are continuous in the closed interval a comma b up to nth derivative. Similarly, the derivative of f of x up to nth derivative are differentiable in the open interval a comma b. Then there exists a real number which lies in between a and b such that the expansion of f of b with respect to a is given by f of b equal to f of a plus b minus a into f dash of a plus b minus a whole square by 2 factorial into f double dash of a, etc. up to b minus a whole to the power of n minus 1 by n minus 1 factorial into n minus 1th derivative at a plus the remainder b minus a whole to the power of n by n factorial into nth derivative at c. We know this, and we know that we can rewrite this one. Instead of taking the interval from a to b, if we take the interval as x naught to x, then it can be rewritten like this. That means the expansion can be rewritten as f of x equal to f of x naught plus x minus x naught into f dash of x naught plus x minus x naught whole square by 2 factorial into f double dash of x naught, etc. x minus x naught whole to the power of n minus 1 by n minus 1 factorial into n minus 1 the derivative at x naught plus x minus x naught whole to the power of n by n factorial into nth derivative at c, where c is a point which lies in between x naught and x, and the remaining condition, the conditions of Taylor's theorem holds good with an assumption that it is satisfying this, and we are written this. But we know what is the Taylor's infinite series expansion is. When you consider Taylor's infinite series expansion at x equal to x naught, right, it will, instead of a finite number of terms, you'll have infinitely many, and it goes on continuous. So that is given by f of x equal to f of x naught plus x minus x naught into f dash of x naught, etc. It goes on continuous, right? Now similarly, we knew what is the Maclaurin's infinite series expansion is. The Maclaurin series expansion is, here in the Taylor series we'll be finding the expansion of f of x at the point x naught, whereas in the case of Maclaurin series expansion, we'll find f of x at x equal to 0. Instead of x naught, we'll consider x equal to 0. So just we have to replace wherever x naught is there in the Taylor's infinite series by 0. So you'll get f of x equal to f of 0 plus x minus 0 is x into f dash of 0 plus x square by 2 factorial into f double dash of 0, etc. Right? Then what is the Maxima syntax for finding the nth order Taylor's polynomial of f of x at x equal to a? Command is very simple. It's a built-in function. You have to write Taylor within simple bracket. First you have to write the function, the given function, comma, then you have to write the variable, right? Then you have to write at which point you are finding the Taylor's polynomial, at the point a, right? Comma, what is the order of the Taylor polynomial or Taylor series? So here nth order, therefore it is n with a semicolon. This gives you the Taylor expansion of f of x at the point x equal to a, consisting of nth degree polynomial, right? Similarly, what is the Maxima syntax for finding the nth order Maclaurin's polynomial of f of x? We know the command is one and the same, Taylor. within simple bracket. First you have to write the function, then you have to write the variable, comma. We know in the case of Maclaurin's polynomial, we find that x equal to 0, right? So you have to write 0. In this case, a may be different in the case of Taylor's, but here in the case of Maclaurin's polynomial, it is always 0. So 0, comma, since it is nth order, we'll write n. So you'll get, when you execute this command, you'll get a Maclaurin series expansion of f of x, which is having nth degree terms. Now, let us see some examples. Write a Maxima program to obtain the Taylor series expansion of f of x at x equal to a. So as usual, we'll write kilol with $sign, then Taylor. What is your given function? It is f of x only. So f of x, comma, variable is x, and at which point you are finding a only, a, comma, say let us find for third order. So let us write 3. You can write anything here. Don't write n because we have to specify what is the n value, because the compiler cannot understand what is that n. So we have to specify what is the number for n. Here I had given 3. So it will display third order Taylor series expansion. Okay. This is the general program. Now let us see one more problem. Write a Maxima program to obtain the Taylor series expansion of f of x equal to e to the power of x at x equal to a, and also solve manually. Now, we'll write the Maxima program for this, and we'll find Taylor series up to the term containing x to the power of 4, right? If they are not specified, generally we'll find here, in our case, the term containing x to the power of 4. Now let us solve manually first. What is your given function? F of x equal to e to the power of x, right? We know what is the Taylor series expansion is. It is f of x equal to f of a plus x minus a into f dash of a plus x minus a whole square by 2 factorial into f double dash of a plus x minus a whole cube by 3 factorial into f triple dash of a plus x minus a whole to the power of 4 by 4 factorial into fourth derivative at a, etc. So for this, we need to find what is our f of a first. What is your f of x? E to the power of x. Therefore, what is your f of a? It is e to the power of a. Then differentiate this. What is the derivative of f of x? Derivative of e to the power of x is e to the power of x. Therefore, f dash of a is e to the power of a. Now differentiate this once again. So derivative of this is again e to the power of x. So f double dash of a is again e to the power of a. Now differentiate e to the power of x once again. You'll get e to the power of x only, f triple dash of x. Therefore, f triple dash at a is equal to e to the power of a only. Then again differentiate this one more time. You'll get fourth derivative of e to the power of x, which is again e to the power of x. Therefore, fourth derivative at a is also e to the power of a. Now substitute all of this in this formula. What is your f of x? It is e to the power of x. What is your f of a? E to the power of a plus x minus a into f dash of a is e to the power of a plus x minus a whole square by 2 factorial into f double dash of a is e to the power of a plus x minus a whole cube by 3 factorial into e to the power of a, that is f triple dash of a, plus x minus a whole to the power of 4 by 4 factorial into e to the power of a. We got this much. Now we can expand this as e to the power of x equal to e to the power of a plus x minus a into e to the power of a, or otherwise you can take e to the power of a outside and you can write, right, divided by 2 factorial is 2, and here 3 factorial is 6, 4 factorial is 24, etc. So this is the expansion of e to the power of x at the point a. Now what is the Maxima program? Kilol. As usual, we'll define a function f of x by assignment operator colon with equal sign, percentage e, because E is built-in function. So percentage E gives you E, natural log E, cap X. Then the command for obtaining the series is Taylor within bracket f of x, variable is x, comma, at which point a, comma, how many, what is the order of the polynomial? 4. So 4 with a semicolon. This gives you the Taylor polynomial of order 4 at the point a. Now we'll see another problem. Write a Maxima program to obtain the Taylor series expansion of f of x equal to tan inverse x at x equal to 1 and also solve manually. So what is your given function? F of x equal to tan inverse x, right? We know we have to find at x equal to 1. So put x equal to 1. You'll get f of 1 equal to tan inverse of 1. What is your tan inverse of 1? Pi by 4. Right? As usual, since they have not specified anything here, till which point we have to find, we'll find up to x to the power of 4. So we have to find fourth order derivative. F dash of x, derivative of tan inverse x is 1 by 1 plus x square. Therefore, f dash of 1 is 1 by 1 plus 1 square, which is 1 by 2. Then what is your f double dash of x? Right? Now send this one to numerator. That becomes 1 plus x square whole to the power of minus 1. Right? So it is of x to the power of n form. What is the derivative of that? Minus 1 into 1 plus x square whole to the power of minus 2 into derivative of 1 plus x square is, derivative of 1 is 0, derivative of x square is 2x. Right? Send that 1 plus x square whole to the power of minus 2 to denominator. That becomes minus 2x by 1 plus x square whole square. Otherwise, you can apply u by v rule also. Denominator square, then denominator into derivative of 1 is 0. So 0 into anything is 0. Minus numerator 1 into derivative of denominator is, derivative of this is 2x. So you'll get minus 2x. Now we need derivative at 1. So put x equal to 1. You'll get minus 2 by 1 plus 1 whole square, which is 1 plus 1 is 2. 2 square is 4. 2 by 4 is 2. So you'll get minus 1 by 2. Now differentiate this again with respect to x. We'll apply u by v rule. Denominator square, denominator into derivative of numerator, derivative of minus 2x is minus 2 minus numerator minus 2x into derivative of denominator 2 into 1 plus x square. Then forget this power. Derivative of 1 plus x square is 2x. Simplify this, you'll get this much. Because in these two, 1 plus x square is common. So 1 plus x square I've taken out. Then remaining is 1 plus x square here. Multiplied by minus 2 becomes minus 2 into 1, minus 2. Minus 2 into x square, minus 2x square. Then minus into minus plus 2x. 2x into 2, 4x. 4x into 2x, 8x square. Simplify, you'll get this. But we need derivative at 1. So put x equal to 1 and x equal to 1 here. So minus 2 plus 6 divided by 1 plus 1. So this is 8, 4 by 8, which is 1 by 2. Now again differentiate this by u by v rule. You'll get fourth order derivative. Denominator square, then denominator into derivative of numerator. Derivative of this is 0, derivative of this is 12x. Minus numerator into derivative of denominator 3 into 1 plus x square whole square. Multiplied by, forget the power, derivative of 1 plus x square is 2x. Now in both of them 1 plus x square whole square is common. Here also present, here also. So 1 plus x square whole square comes out. And 2 3 is a 6. 6 is also common. So I've taken 6 and 1 plus x square whole square common. So when you take 6 outside, this becomes 2x. And since you have taken 1 plus x square whole square outside, 1 plus x square is remaining here. So 2x into 1, 2x, plus 2x into x square, 2x cube. Then this 3 and 2 has come out, 1 plus x square has come out. So x into this, minus into minus plus 2 into x, 2x, minus into plus minus 6x square into x becomes minus 6x cube. You simplify, you'll get this much. but we need the derivative at 1. So put x equal to 1, you'll get 4 minus 4 divided by 1 plus 4. 1 plus 1 whole to the power of 4. 0 by anything is 0. Now let us substitute this in the Taylor's infinite series expansion formula. We know what is the expansion at x equal to 1 for the function f of x. F of x equal to f of 1 plus x minus 1 into f dash of 1 plus x minus 1 whole square by 2 factorial into f double dash of 1, etc. Now substitute all the above results here. What is your f of x? Tan inverse x. What is your f of 1? Pi by 4 plus x minus 1 into f dash of 1 is 1 by 2 plus x minus 1 whole square by 2 factorial into minus 1 by 2 f double dash of 1 plus x minus 1 whole cube by 3 factorial into f triple dash of 1 is 1 by 2 plus x minus 1 by 4 into 4 factorial into f fourth derivative at 1 is 0. Simplify this, right? 2 factorial is 2, 3 factorial is 6, 4 factorial is 24. 24 into 0 into anything is 0. So this goes up. So you'll get this much. So this is the Taylor series expansion of tan inverse x at x equal to 1. Okay. Now let's move on to one more problem. We have to write Maxima program for this. As usual, kilol with dollar sign, f of x with colon and equal sign is equal to, right? We don't need this percentage. This is not necessary, right? This is not needed here. We know how to write tan inverse x because tan inverse x is a tan of x. That's it. Arc tan of x. Right? Then Taylor of f of x, variable x, at which point you are finding? Not a, 1. So 1, comma, up to the order 4. So 4. This gives you Taylor's infinite series expansion of f of x at the point x equal to 1, right? Till the term containing x to the power of 4. Now, let us move on to one more problem. Write a Maxima program to obtain the Maclaurin series expansion of log of 1 plus x up to the term containing x to the power of 4 and also solve manually. So we have to write Maclaurin series expansion. That means our a will be 0. So we have to find the series expansion, Taylor series expansion only, but at the point 0. Am I right? Okay. Now let us call this one as f of x. So we have to find f of 0 first. F of 0 equal to log of 1 plus 0 and log 1 is 0. Then differentiate log. You'll get 1 by 1 plus x. That is your f dash of x. At 0 means 1 by 1 plus 0, which is 1. Then f double dash of x. Send this one to numerator. That becomes to the power of minus 1. So 1 plus x. So this becomes, if you send numerator, this becomes 1 plus x whole to the power of minus 1. This is of the form x to the power of n. So we can differentiate this minus 1 into 1 plus x whole to the power of minus 1, which becomes minus 2. So if you send this one to denominator, that becomes 1 by 1 plus x whole square with minus sign. Therefore, f double dash of 0 is minus 1 by 1 plus 0 whole square, which gives you minus 1. Now again differentiate this. Again send this one to numerator. This becomes 1 plus x whole to the power of minus 2. So minus 2 into minus becomes plus 2 into 1 plus x whole to the power of minus 2 minus 1. That is minus 3. If you send it to denominator, that becomes plus 3 like this. But what is your f triple dash of 0? F triple dash of x at 0? 2 by 1 plus 0 whole cube, which is 2. Again send this one to numerator. That becomes 1 plus x whole to the power of minus 3. Alright? Then derivative of this is minus 3 into 2 becomes minus 6. Minus 3 minus 1. That is minus 4. Send this one to denominator. That becomes plus 4. But we need this at 0. So at 0, if you put x equal to 0, you'll get minus 6. Now, what is the Maclaurin's infinite series expansion? It is f of x equal to f of 0 plus x into f dash of 0 plus x square by 2 factorial into f double dash of 0, etc. Because your a is 0, you will not get x minus a. Simply you will get x in these terms. So what is your f of x? Log of 1 plus x equal to f of 0 is 0 plus x into f dash of 0, 1 plus x square by 2 into minus 1 plus x cube by 6, because it is 3 factorial. 6 into 2 plus x to the power of 4 by 4 factorial is 24 into minus 6, etc. If you simplify, you'll get this much. So this is the Maclaurin series expansion of log of 1 plus x. Now what is the Maxima program for this? As usual, we start with kilol f of x. It's a function, therefore we have to use functional assignment operator, that is colon with equal sign log of 1 plus x. Then Taylor, the function is f of x, comma variable x, comma at which point you are finding 0, comma up to the order 4. So 4, put a semicolon. This gives you the Taylor series expansion of this. Now let us move on to one more problem. Write a Maxima program to obtain the Maclaurin series expansion of log of secant x up to the term containing x to the power of 4. Not necessarily they may give always x to the power of 4. They may give x cube to the term containing x cube. Then you have to find up to third order derivative. X to the power of 5. Then you have to find up to fifth order derivative. X to the power of 6. Then you have to find the sixth derivative. So depending on this, we have to find the number of derivatives. Now, what is your f of x? Your f of x is log of secant x. We need f of 0 first. So log of 1 plus, oh sorry, this is not 1 plus, log of secant 0. Log of secant 0. What is your secant 0? It is 1. So log of 1 is 0. Log of 1 is 0. It is simply 1, log 1, right? Now, differentiate this with respect to x. So outside function is log. So what is the derivative of log? 1 by of this term. So 1 by secant x. Now forget log. What is the derivative of secant x? Secant x into tan x. Now these two get cancelled. You will get tan x. So what is the derivative at 0? Tan 0. And tan 0 is 0. Now differentiate this again. Derivative of tan x is secant square x. So f double dash of x at 0 is secant square 0. And secant 0 is 1. Because secant is 1 by cos. And cos 0 is 1. So 1 by 1. 1. 1 square is 1. Now differentiate this. So it is of the form x to the power of n. So n into, that is 2 into, derivative of 2 into secant x. Now forget the power. Derivative of secant x is secant x into tan x. So this gives you 2 secant square x into tan x. But derivative at 0 is 2 secant square 0 into tan 0. And tan 0 is 0. 0 into anything is 0. Now apply the product rule for this by keeping 2 constant outside. 2 into, keep secant square x as it is. Derivative of tan x is secant square x. Plus keep tan x as it is. Derivative of this. First you have to differentiate, assuming this is of the form x to the power of n. X to the power of n. What is the derivative of x to the power of n? N into x to the power of n minus 1. That is secant to the power of 2 minus 1. 2 minus 1 is 1. So you will get 2 secant x. Now forget this power. Derivative of secant x is secant x into tan x by chain rule. Now if you simplify, you will get this much. But we need fourth order derivative at 0. So put x equal to 0 and tan 0 will be 0. 0 into anything is 0. Secant 0 is 1. So 1 into 2 is 2. Now we know that the Maclaurin's infinite series expansion of f of x is, as usual, standard formula, f of x equal to f of 0 plus x into f dash of 0 plus x square by 2 factorial into f double dash of 0, etc. Substitute all these in this, we'll get f of x equal to log secant x is equal to f of 0 is 0 plus x into f dash of 0 is 0 plus x square by 2 factorial is 2 into f double dash of 0 is 1 plus x cube by 3 factorial is 6 into f triple dash of x is 0 is 0 plus x to the power of 4 by 4 factorial is 24 multiplied by fourth derivative at 0 is 2. Now you simplify, you'll get this. And writing the Maxima program is very simple. Kilol, and you assign the function f of x colon with equal sign log of secant of x, and we want to display this. That's why we are given semicolon here. If you don't want to display the output, then you put dollar sign. It executes, it stores f of x with this value, but it will not be displayed. Taylor of f of x comma x, and at which point, because it's a Maclaurin series, you have to give a as 0 comma, and since it is up to the power 4, that is x to the power 4, so 4 only. If it is 6, then we'll give here 6. If it is up to x to the power 5, then we'll give 5 here, right? I've given few more problems. You write the Maxima program and also solve them manually, both the Taylor series expansion and Maclaurin series expansion of the given problems, and write them as assignment. We'll continue and we'll solve this using Maxima. ಕೇಳಿಸ್ತಿದೆಯೇನ್ರಪ್ಪ?